Hello, I'm Kang Choi from Yonsei University. I will talk about our zero-shot quantization paper called AIT. First of all, zero-shot quantization means that neural network quantization without the original dataset. The accessibility of the original dataset is essential to the quantization for preserving performance as much as possible. However, in real-world scenarios, the original dataset is often inaccessible due to privacy, protection, copyrights, etc. Therefore, zero-shot quantization targets the situation where we only have pre-trained neural network. To fine-tune quantized network, many methods apply teacher-student knowledge distillation method by setting full precision network as a teacher and quantized network as a student. In addition to that, to reproduce unseen dataset, GAN-like generator creates synthetic samples for the training. In this circumstance, we focused on the loss function. To train quantized student, loss function is a linear combination of cross-entropy loss and KL divergence loss. However, these loss function choices were adapted from the KD task without considering synthetic sample training or the quantization. So, our first question was, do KL and C losses cooperate on zero-shot quantization? To find the answer, we decided to measure cosine similarity between gradients of KL and CE. And the answer was no. Contrary to ordinary knowledge distillation, the gradient direction formed an obtuse angle. That means KL and CE are not cooperating with each other and may cause performance degradation. Therefore, our second question was, what loss function do we need to choose? The hint was found in generalization in neural network. The generalizability of neural network is a crucial point, especially if you use only synthetic samples for training. Many papers pointed out that flatter local minima are connected to better generalization. To measure flatness of local minima, we can use trace of Hessian matrix of each loss. The experiment results show that trace of cross-entropy loss is order of magnitude larger than that of KL divergence. Going one step further, we visualized loss surface itself. The right side figure shows that KL divergence has much flatter loss surface. In conclusion, we decided to use KL divergence only for training. Disappointingly, the results were far different from our expectations. No settings were improved compared to the baseline. The reason was found in another aspect of zero-shot quantization, which is quantization itself. As you can see in the left figure, small gradient update of floating point weight cannot make changes to quantized weights. Therefore, weak gradient updates make imbalanced updates per layer, or even no updates on certain layers. To solve this issue, we propose quantization-aware gradient boosting method called gradient inundation. Gradient inundation is designed to ensure a certain portion of updates for quantized weights. By applying GI to KL-only training, we achieved balanced and steady training for quantized network. As a result, AIT shows significant improvement in many settings. For example, 4-bit quantization on ImageNet dataset, AIT shows the best performance among existing works, regardless of target networks. To summarize, we analyzed loss functions of zero-shot quantization from multiple perspectives, and emphasized flatter loss minima. And then we inspect current limitations of zero-shot quantization training. In conclusion, we proposed GI that ensures balanced weight updates among all layers. For the more details, you may find us in poster session or refer to the paper. Thank you for listening.